Hello, good morning. I am Najib from ISAE-ENSMA, France. First of all, I would like to thank all the organizers of ICAS conference for giving me this opportunity to present my work that I am doing in my research group, model and data engineering. This work is mainly focused in the integration of energy consumption in database. And this project is funded by an European funding improvement. Let me start with the context of this presentation. If you Google now using this simultaneously these three words, COVID, climate change, you can find easily more than 185,000 results. Why this big number? Because many people are linking COVID and climate change. This climate change concerns many sectors. As you know, we can have transportation, housing, services, IT. And all people now, all researchers, all institution, they are trying to work in energy efficiency in each sectors. What does it mean energy efficiency? It means that the achievement of the same level of services while consuming less energy. And nowadays, climate change is everyone business. And that's why we fund many green initiatives from individuals to international institutions. For example, if I take the case of individuals that are, if we see in France for the last election, the Green Party won the election because all people are are thinking about the green initiative to change our planets. And since we are scientists, let's see what are the place of scientists in climate change. I think climate change is a great opportunity for scientists in terms of funding, research topics, and collaborations. And if you take a look up to, for example, to European Commission plan, they fix very well-identified quantitative objective to reduce, this, the energy consumption and the usage of renewable energy. And they are giving, recommendation and orientation for, individuals and companies, institutions to achieve this objective. Let me give you an example of a European project that where I am involved about zero energy building into a public building, and I will share with you my experience and why this project motivates me to work in energy in database. This project is involve many partners from Spain, Portugal, and France, and we are studying hospital in Spain to make it zero energy building. And then for this project, we are intensively using data based solutions to make this building smart. And then we are proposing, we propose this solutions, this methodology to, to get the data from the building, from the hospital actors and the weather. And then we take this information, then we store this information in a storage device, and then we run machine learning algorithm, statistic, data mining to get some recommendation for the government and the region politics. And then when I did this work, I get some feedbacks, and I would like to share with you these feedbacks as database researcher. This smart building community is well-established communities because this one has many high-ranked journals. And when they try to integrate energy efficiency in their work, they use audit, and then they try to audit all components, all the ecosystem of buildings to get some hints to reduce the energy. For example, they are looking for materials used in the constructions. They are using the whole cooling, heating, ventilation systems and infrastructures, the behavior of the building user, and then they are using data-driven solution based in machine learning and deep learning solutions. And then I start thinking how we can reproduce, how we can generalize this experience in database community at the research and teaching levels. Then to do this, I would like to share with you how you can reproduce this in your research. It is the basic idea about this presentation. To do this, I try to do a SWOT analysis for database community. Then I start with the strengths of these communities. As you know, it is well-established communities that we find many solid theory, like theoretical, relation algebra, transaction processing, and it is a committee which provides for tuning awards in each decade, starting from 17, which is the date where the database emerged. And we find many DBMS in the market, and we have a lot of open source DBMS, and database, it has one important characteristic. It is that database is taught in all disciplines. We can teach database in university, in literature, in computer science, in medicine, in law, and we can find it everywhere. And we have many open source systems that we can use in teaching and in our research. For example, I give you this figure about this DB engine, which website that ranks DBMS based in their usage in the industry. We'll find easily, PostgreSQL in 4th level. And weakness of this database technology, according energy, it is we don't teach enough. We don't teach enough energy culture in our course. We teach only performance. We do SQL queries to get efficient results and how to speed up the queries that we have. The opportunities. I think we have nice opportunities in database now. It is, there are many opportunities that I can classify in maybe 6 points. The first important point is big data and machine learning stuff, because we have a lot of data, and automatically, since we have a lot of data that becomes the new oil, then we have to care about the new CO2 generated by this data. And then we have a lot of effort in terms of research and industry about emerging hardwares, cloud, and virtualization. And in database, we have many steps that can be used to see how we can integrate energy. For example, in exploitation layer, in optimization layer, maybe we can find some issues to how to integrate energy. And then we have a lot of fundings. If we think about energy in database, I think we have a lot of findings where we can build a nice project to get this money. And another opportunity is the availability of open source DBMS and even more open source big data and machine learning frameworks. The threats of database is that many people actually they are demanding high performance because we have like some big category of application which concern decision making where people are looking for performance. And the second point is about the complexity of database. Now database can become like a complex system which integrates many aspects like software, hardware, network, coding, and all this information. and the absence of this multidisciplinary vision in our teaching activities. Okay, then when I did this job in terms of analyzing, I did another analysis to see what is the place of green computing or green topics in database communities, and I choose two conferences where I am involved. It is the DAWAC conference and the DOLAP workshop, which are mainly data warehousing and business intelligence and big data application, where we have a lot, we have the data, the volume of data important. And then I try to generate the main topics from this conference from academicmicroprofessor.com, and then I get these topics, and then I draw my cloud work to find, you know, what is the tendency. What is the tendency of these communities? And then we find that we have a lot of topics, and one topic which is important, it is query performance processing. Okay, and if we analyze this figure, we don't find any word about green staff, energy, nothing. Okay, and then the basic idea is that we have to move from performance-oriented to energy-oriented query processing. You know, instead of giving more importance to query processing or query performance, we try to replace it by energy processing. Why? Because energy, it is, I mean, it concerns all, you know, the component of your machine. It concerns, you know, CPU, disk, and mid memory when you are using your machine. Okay, and then the most important component of your DBMS or your database is the query processor, because you have to process the queries. And when we start doing this, we start, you know, looking about the literature, and we find one most popular opinion saying that operating system or operating system or hardware should manage energy of query processing, and they leave data systems as a second priority. What doesn't mean that there are many people, many researchers, especially from Asia, they are just pushing hardware solution instead of pushing software solution, because he said, okay, if we have energy efficient hardware, then we can reduce energy. And then we start working in these issues. Okay, maybe we can have like combined solution, because, you know, this software, this hardware works with and they are controlled by software. And then we try to see how software can be used and combined with the hardware solutions. And how we can do this, we propose this this methodology that we call it auditing power before deploying. It is very important. I mean, we are inspired from building community, smart building community. We have to audit something and then find, you know, all energy sensitive component, and then we can do state of art of this of the work behind this query processor, and then we can model energy and estimate it. And then if we have all the theory established, then we can deploy in systems and having some validation. Okay. Then I will start with the agenda of my presentation. The first of all, I will try to audit the query processor, and then I have to show you the state of art about these topics. Then I show you how we model energy using machine learning algorithms, and then how we deploy this solution, and then I conclude with the summary. I think, you know, this picture, you can find it in all database textbook, you know, about query processor component. You know, when you, it is like when you run your Java code, when you run your SQL code, it is the same. You have your SQL, and then your SQL has to be compiled and then has to be checked in semantically and syntactically, and then you have to call the query optimizer to find, the best solution. And then you get when you have the best plane, you go and then you get the data from your disk, and then you run your queries. Okay. Then I give you an example about queries, especially analytical queries. Then you have this kind of star schema benchmark, and then you have these complex queries. Why we are dealing with these complex queries? Because they involve many operations like join and selection, and these operations are data intensive computations. Okay, and then the basic idea is that how we can optimize these queries. It is the current research work. All people, they are trying to optimize these queries, but we try to see how we can reduce energy of these queries. Okay, and then if you go further, then when you have this query, then you generate query trees. And query, it is a tree where we find a table at low level, and then we have the nodes, and each node is correspond to a selection or join or a union operation. And basically, this query tree is not unique. You can generate a lot of similar query trees which have the same result, but it's not the same cost in terms of query processing. Why we have this? Because we have these properties in relational algebra, like a commutation of the selection, associative of the join. That's why we can generate multiple query plane. Query tree. And now from this query tree, we generate query plane. And what does it mean query plane? It means that for each node, we have to associate the implementation of this operation. For example, if we have the selection, we have to deal what is the nature of the selection that we are using. It is sequential selection or index selection. If I have join, as you know, we have many implementation of the join. Then I can use nested loop, sort, merge join, hash join. And each implementation has its own cost, okay? And to estimate this cost, the database people, they are building cost model to get in estimation. And here, I will show you, the hardness of query optimizer. Why it is hard? Because, for each plane, you have to estimate its costs, and then you have to generate all possible planes for your queries. But because your query has several planes, and people, they are in actual vision, people are demanding speedy access to data no matter how the complex query are. And finding the best query plan, it's an NP hard problem. That's why there are many efforts in developing dynamic programming algorithm and greedy heuristics. And how we can estimate this this energy? This energy is estimated using a cost model. A cost model, it is a function that estimate, for example, your query cost. What is the cost of my queries? Okay. Then how we build these cost models? Since your queries is a composition of several operation, then we have to deal with the one operation and then estimate its cost, and then we can generate this to get the the global cost. And for the metrics, you have many metrics. As I said before, you have input IO metrics, CPU metrics, or network metrics. And then to have this estimation, you need some parameters from database, DBMS, query, platform, hardware. And then the signature of your cost model by operation is that you need some properties, and then you get some values. And then you have some hypotheses. For example, the hypothesis that we teach in the school is that we support that, for example, we have a uniform distribution of attribute values. Let me give you an example how to do this estimation. Suppose that I need to estimate the number of IO and then the number of page to execute this following query. Select star from T. To do this, if I am in row store implementation, then in database we suppose that the data are in your disk, and then when you ask for a query, the data has to be loaded from your disk to your main memory. And to do this, you know, we can get this formula easily. Then if I have to load, you know, the number of page of my table T, and the number of page is the cardinal of my my table times the length of each instance, divide by block size of my page disk, and then I get estimation about, you know, the number of page that has to be loaded from my disk to my main memory. And then if I have the time for loading one page, I can easily compute the time of my query. Okay. And then here I give you an example of query optimizer component. Then it is like this. You know, you have your queries. Your query has to be passed, and then you generate your Russian algebra, and then you do the optimization. You have many plans. You have this cost model. The cost model uses some statistic from your database, and then you have like search strategy like genetic algorithms or linear programming, and then you generate the best solution according to target metrics. Okay, and then the basic idea is how we can make this this query optimizer green. I mean, instead of having, you know, performance, high performance, I would like to have less energy. It is the main issue. How we can do this? First of all, we need to know some basic concept about power and energy. And power is the rate of doing work, or energy per unit of time. And energy is the ability to do work. And then you have these basic formulas. And in the literature, when people work with energy, they have many type of energy or power. You have the baseline power, active power, peak power, and average power. In our work, we are using this average power when we execute queries. Okay. Okay, let's do a state of art of this nice topic. You know, when we try to look the literature with my students, we figure out that there are many works, especially based in hardware, you know, aspect. And then if we integrate, you know, energy efficiency in database, we can find easily two levels. One level, we call it system level, and another level is called it environment level. In system level, we have two parts. Because in your system, you have the hardware part and the software part. In hardware part, you have many solution about power management, data storage solution, dynamic voltage and the frequency scaling. When you do your I/O, if you are executing a query, maybe you can stop your I/O device then to save some energy. In software techniques, there are people working in data model. How we can model, you know, the energy of your query processor to capture, you know, and to estimate this energy. And another direction, people, they are playing with different algorithms for implementing, for example, selection, join, to see which kind of algorithms that provides less energy. And for the second part about the environment level, yeah, then you have this information about, you know, the sources that you are using for your energy provider, and all this cooling and the cooling infrastructure for your database manager and user awareness. And then you have other demos about networking and cloud and virtualization techniques. Then when we start with this, I ask my student to make me like a roadmap, you know, to help students to work in these topics, and then to see what is the preference of each student start working. For example, if you want working about, you know, software solution, you come from here, and then you can find, you know, all work done in this topic. For example, in software-based solutions, there are many people working in modeling level about the queries or pipeline or operator. Because when you try to think about, you know, energy efficiency of queries, the question is that do you consider the energy at query level or at operation level or at pipeline level? There are many studies about this, and there are many research work about, you know, the definition of cost model to estimate energy using different machine learning techniques. And there are other work about, you know, query processing, buffer management, and the parallel database. And you have another direction about, you know, hardware. And here you find all solution about, you know, the usage of volatile memory, CPU, doing co-processing about CPU, GPU, storage management, and even all solutions that concern, you know, the hardware and device, and, you know, even your screen, the screen used for your computer, and all this information. And then you have another direction about, you know, the tools that we can find in these topics. And then we have very nice vision paper that I recommend to students to take a look to get more knowledge from these papers. And then to do this, you know, I ask my student to identify what the parameter that I can use to build my my models. What are the energy sensitive parameters from database that I have to use to capture the energy? And then we give these classifications. We have parameters that cover DBMS, query parameters, hardware parameters, architecture parameters, and then we have, you know, the type of your database. If a database is relational or relational, buffer management. What is the algorithm that are using? Do you use a FIFO algorithm or LRU? And the storage layer, if your database is row-oriented storage or column-oriented storage, different optimization techniques. Are you using materialized view, partitioning, indices? What are the implementation of your algorithms? What are the devices? Are you using GPU, CPU? What is the device storage device type? Are you using HDD or SSD? What are the platforms that the platforms that you use for deploying your DBMS and all this information? And then that's why it is a complex problem, because you need to choose the relevant parameters that help you to capture this energy. And how we estimate energy, it is same. It is like in query performance. The people, they are doing the same. They are following the same methodology as in the previous work, but they are integrating energy. I mean, in query performance, people, they are just taking into account I/O cost. They assume that CPU cost is not important. But when you do energy processing, you have to deal with the three components: CPU, input, IOs, and network. And then we have to reproduce the same strategy. For each operator, we have to estimate the energy, and then we do the composition to get the final consumption. For example, here I give you an example of this cost model proposed by Xiu in 2013. You know, you have your tree here, and then I mean, when you load your cell table, you pay 3 watts, and then you have to accumulate all this cost to get, you know, the final cost. And the basic idea is that they are using the same data structure as I showed you before, query trees, and then they are building their cost model. Okay. Then our methodology to do this work, you know, as I told you before, our methodology is based in audit aspect. Then I have to audit my system. I get all the relevant information. And then I have to build. I have to know how my queries are executed. What are the modeling used by my DBMS, and then I have to get the value of these parameters, because I have parameters, but I have to know what are the different value. You know, it is like in smart building. Then when I get the parameters from machine learning techniques, then I can set up these parameters, and then I validate this model in some system to see the energy consumption of my DBMS. And here I give you, the philosophy of our green query optimizer. Yeah, it is composed in two parts. One part, we call it offline part, that we get all these parameters using machine learning techniques, and then this parameter, then I get my model, and then I put my model in my DBMS, and then I watch, the behavior of my DBMS in terms of energy. And then I need some tools. It is like in building, because people that do in building, they have tools that allow you to observe, the consumption of your buildings. You can tune, you can monitor your building to reduce this energy. And then we have the same inspiration from the building, and then we put it in our database. And to do this, then this problem is that you have to choose. We have to choose the target DBMS. As you see, we have proposed, like generic solution. Then we have to instantiate this generic solution in some target DBMS, and we choose for this. We choose Postgres DBMS. Why with this choice? As I show you before, it is the ranked top 4 in this ranked DBMS in the market. And especially it is widely used in research and teaching, especially for OLTP application, okay? And then I have to show you a basic audit. This system use row-oriented storage layout. What does it mean? It means that one instance is stored in your disk, one line by line, okay? For example, if I have this table, one CMO, male and 36, this information has to be stored in one page of your disk. We call this row-oriented storage. And the Postgres is only for SQL queries. And we choose the multi-core of Postgres because Postgres has two implementation, one with one core and another one with the multi-core. And the modeling level in Postgres is a pipeline. I will show you just after these slides. The pipeline, it is work at operation, but using the pipeline. And you can find other parameters, for example, the type of index that are used in DBMS, the selectivity of predicates, the buffer politics, all the information that you have in your DBMS, then you get this DBMS. And since this DBMS is open source, then I can get easily this information from the code of this language. Okay, and my energy cost here is only CPU and IO, because I am in centralized environment. I am not using network. Okay, and now for the pipeline. So the pipeline is very important. We spend 1 year to understand, that the system is working in pipeline, because when you do join, or when you have queries, which is composed by selection and the join, I mean, the system will not do selection and then the join. It can do many operations in pipeline, and then you have to understand how the pipeline is done to get the energy. That's why we spend 1 year, and then we get this information about the pipeline, and we publish this information because we know this. Knowing this pipeline work, then you can estimate energy. As I show you here, when a query execution goes from one pipeline to another pipeline, its energy consumption change. Because it is not one pipeline, it is not one block. It is one pipeline to and after each change, you can change your energy. And then when I get all this information, and then we build the machine learning techniques, and based it in these formulas. The power of a query, it is the sum of the power of each operation for each pipeline, because we are working in pipelines, and times, you know, the time of each pipeline. It is the power, okay, power formulas. And then we have to know what is the real power for each pipeline. And for this, we have to use machine learning techniques to get these different parameters, which are W CPU, W mean memory, and W IO. D'accord? And then we get, you know, these parameters that we have here. This parameter we have here. Usually, if this one, I can get them from the Postgres system, because I can system can provide me this information. And for this, we ran many algorithms of machine learning, and then we find multiple polynomial regression that fit our model. Okay, and then we have this kind of equation that we get after, you know, training the system using more than 100 queries to get all these parameters. Okay, and then we use another deployment. I mean, we use another DBMS which is called MoniDB. It's a system open source, like Postgres, but it is mainly for analytical queries, and it is using column-oriented storage instead of row storage. What does it mean? Each column is stored in each attribute is stored in one column. And then, for example, here we have 4 columns and with 4 storage layout. Okay, and this system, since we have these different columns for each instance, then we can do the compression. The compression can do it at the memory level or at disk level. And this MoniDB support many other query language, like Sparkle language. And then we have like Postgres, multi-core, and the modeling level is operation. It doesn't work in pipeline, it's working in operation. And then we have the same, you know, energy cost. And then we have to do the same effort. And here the change is that here, you know, this information, these 2 information are provided from MoniDB, but here we are using this processor counter monitor to get the execution. We are using this external resources to get the estimation of the number of instructions executed by your CPU. Okay, and then we did the same effort, and then we get this multiple polynomial regression with degree 3. Why degree 3? Because degree 3, I think it allows us to capture, you know, the interaction between different parameters. And then now we have, you know, our models, we have everything, and then we took these models and then we put them in both in MoniDB and PostgreSQL to capture energies. And then we have this, we buy this the WhatsApp power meters to capture these energies. And this power meter is connected to your server, and then we collect the information like this. And then the first result that I would like to share with you is that the MoniDB is good in terms of query performance and even energy, and it outperforms Postgres in energy. And what is the interpretation of this? It is, I think, the high compressed, you know, data, and especially the column store. And then that's why, you know, I mean, it provides very nice, you know, energy saving. And then, for example, to give you hints, for example, if you are a company, this result will, if you are looking for a climate change, or you are climate change sensitive, you can easily use MoniDB to deploy your application, for example. Okay. And here since MoniDB is good, then we try to evaluate, you know, the quality of our cost model in MoniDB using this TCP/H benchmark, and then we are computing these relative errors about, you know, the real energy that we get from the power meters and the estimated energy that we get from our theoretical cost model. And then we have an average error is very small. except for these two queries, which is, I think we are thinking they are due to the external tool that you are using to estimate, the CPU instructions. Then now we are using another tool, and we will evaluate maybe if we will see if we get some reduction or not. Okay, here we arrive to our tool. Since as I told you before, we follow the same methodology as in smart building, where we have to provide the tool to see the energy evolution, and then we can monitor this consumption. And then we developed a tool. I have this video in YouTube. Then you can play with it. And all sources of this tool is available in our LIAS Forge. You can go there and download this our project about Postgres Green. I would like to show you just some figures about this tool. Then you have this kind of interface when you can select the host name, the name of the database, and then you connect to your system, and then you have all the information about the energy. And here, I think that I didn't mention in my presentation is that we have we can set up the trade-off weight between energy and performance. I mean, it is up to the company. If you are choosing performance, then you can put power 0. If you are choosing power, you have to put 0 to performance, or you can find a nice compromise between both non-functional requirements. And then you can access your system. You have this kind of interface when you can write your queries, and you get all information about the queries. And then you can see, you can execute your query to see, the power consumption, for example. And then you can see, different, evolution of your database. And then even more, you can see, the pipeline, the different pipeline that I discussed before, that we use to predict this energy. Okay. Okay, now let me conclude my presentation. By this presentation, I try to convince you to add green label in your research by using this auditing power before deploying methodology to apply it in your research. And then we did a lot of effort in energy modeling, identification of relevant parameters to capture the energy and to estimate it for query processor. And we deploy our solution and our funding in two major open source DBMS, which are Postgres, SQL, and MongoDB. One is row-oriented storage, and the second one is row-oriented storage. And we validate our proposal, and we have the tool. I think we have well-finished work that cover, all aspects, of research staff. And now we are working in integrating other parameters like building temperature, using other, deep learning techniques. And I think it is very nice if we can integrate energy to other phase of database design, for example, in conceptual level or even in ETL, where we process a large amount of data. And maybe we have to integrate, the source of energy like solar, which is less energy compared to other sources. I would like to thank my students. Some are already graduate, like Amin Roux, Selma Bouar, and Hassan Boukharsa. And actually, we have two PhD students working in their thesis, Isaac Garbi and Simon Pierre Dembele. Simon Pierre Dembele did work about MongoDB, and Isam is working in optimization structure like indices. I would like to thank my colleagues, Stéphane, Jean, Michael Baron from my team in Poitiers, and Nikos from Greece, Seador from Estonia, and Carlos Ordonez from Houston University. Here we have some green paper about this work. I think we did a nice job. We published all this aspect that I present you in very well-known conference and journals. Thank you very much for listening. And then if you have questions, don't hesitate. Thank you.